DNA identification as an information science. Next slide, please. So for context, why are we interested in DNA? For evidence, DNA helps us solve crimes and to match evidence to suspects and provide a weight of evidence that there's some connection within a crime. For investigative purposes, it's good to have a DNA database of crimes and criminals so that the DNA can reach out across the ether into this collection of possible candidate suspects and thereby make an identification which can be used to match evidence to a convicted offender. And then for crime prevention, which was a vision that America's working toward, that the British began about 10 years ago, and was nicely described in Ray Wickenheiser's article, The Business Case for DNA, 8 years ago, that if all evidence is processed, property crimes, sexual assault, and so on, and all criminals, felonies, misdemeanors, whatever, are promptly put onto DNA databases, then DNA databases can interrupt criminal careers and prevent further crime and prevent victimization. And I think that's sort of the overall goal of people here, is not just how to apprehend and convict criminals, but how to prevent further victimization. So that's why, thank you. Next slide. So the DNA evidence problem, though, is that even though somebody would like to say something very definite in court, this is absolutely a match between these two items of evidence or an evidence of a suspect, most DNA evidence actually is uncertain, with the result that genotypes can be uncertain. We see this with mixtures where there are two or more contributors. For example, here there are 4 peaks, and many methods of interpretation like CPI would produce a list of 10 possible allele pairs reflecting that uncertainty. DNA can be degraded or damaged. We can have low template DNA amounts. For example, here's a peak height around 50. Different people might do different things. So there's uncertainty in what do you do with the quantitative data. So about 10 or 15, next slide. So about 10 or 15 years ago, an interim approach, as John Buckleton calls it, and had published on it, of applying thresholds to the quantitative data was introduced. Now, thresholds have the advantages of simplicity, easy explanation, and being easy to apply. However, they do come with some drawbacks. This is what a threshold does. You pick a level, say 50 RFU, 100, whatever your laboratory determines will be uniformly applied to data of that class. And the threshold is applied, and every peak, there are some second-order decisions, but for the most part, every peak that's above the threshold is considered to be an allele and given uniform treatment, and those peaks which fall below threshold are considered to not be alleles. And so the quantitative data are reduced to a series of all or none decisions as to what's in or what's not, and the quantitative data is then not used with the information that some peak heights might be much greater than others, reflecting more mass, more quantity. So here are some of the issues that are well known. Peak heights have variation, whereas thresholds, I've color-coded this. If you're colorblind, the red is on the right. Okay. Whereas an absolute value may not reflect the fact that there's variation, say, in the vicinity of where a threshold might be. There's an issue of variance scaling. The probability models that have been published for the last 20 years, theoretical and empirical, show that the peak variation, the variance scales linearly with the peak height. It's not a fixed value. It's not constant. Data has probability distributions, as you know, whenever you do replicate amplifications, that the peak heights don't come out the same ever, because they can't. You're drawing from a probability distribution, and that can lead to a high false negative rate when you have higher thresholds. We've done some studies on this showing that the number of missed alleles per locus can exceed 100% with imbalanced alleles. Probability methods that make more use of the quantitative data, as I'll show in a picture in just a few minutes, can concentrate the probability more around the allele pairs that the data is trying to tell you, Whereas if you don't use the quantitative data but treat it qualitatively, that can disperse the probability to other allele pairs that may be far less likely given the quantitative data. With the result being that the information that can be preserved using probability methods on quantitative data is discarded. And these sorts of issues were nicely discussed in the ISFG article by Gill, Prince et al. In 2006. The result, though, is that if you're not preserving evidence, then identifications may fail instead of succeed, with the result that the ability of science to protect society and reduce victimization is worse rather than better. So that's Interim Approach. And in the last 10 years, we've seen progress along the fronts of probability modeling of quantitative data, as well as what to do with that information as measured by likelihood ratios. So I'll give a quick historical background to that of what probability and information mean throughout science and in DNA. Next slide, please. So for probabilistic science, one of the classic examples from the 20th century is Newtonian physics, invented about 350 years ago, and has done a fantastic job for building buildings, bombs, and all sorts of things. Newtonian physics is one of the smashing successes of modern science. However, as the detection got better and electrons were discovered and particles got smaller, the theory didn't work at that submolecular level, or even the molecular level, the way it might have. And when they ran into these issues, Niels Bohr proposed in 1913 what he at the time viewed as an interim solution, which was electrons live in orbitals. And that theory did a lot. It explains some of the early quantum effects. But in fact, it took Schrodinger, Heisenberg, Dirac, and others a good deal of more theory to bring in a probabilistic model in which 12 years later, 1925, was the true solution as far as we know, that electrons come with probabilities. They don't live in discrete orbitals. There's no threshold of where you might be in a particular energy level. They're just diffuse. And that probability theory had some difficulty getting accepted, but fortunately, next slide, at least fortunately for quantum mechanics, the theory was validated by building the atom bomb. Because the theory of probability and probabilistic electrons was able to account for, predict, and help engineer the splitting of the uranium atom, which had the result, by bringing together maybe half of the known physicists and mathematicians and eventual computer scientists in the Western world at that time, ultimately the end of the war in the Pacific, as this was used. And that was a definite validation that quantum mechanics was here to stay and probabilistic methods worked. Next slide. Interestingly, the same methods that were used during World War II and developed by the likes of Fermi, John von Neumann, and other physicists who were mathematicians and the eventual computer scientists, they built the first digital computers during the war, as primitive as they were, and they used them to make calculations. The first calculations ever done on a computer, for this sort of sophisticated scientific effort, were Monte Carlo methods, random probabilistic searching to solve very hard physics equations. The classic paper Metropolis et al. 1951 that describes how you can use probabilistic methods to solve complex, apparently deterministic problems, one of the most referenced papers in all of science. And these sorts of Markov chain Monte Carlo or statistical search methods are now ubiquitous. They're used in every field of science. They're normative science. If you look at the Journal of the American, the Journal of the Association, German American Society, JASA, I forget what it's, I just kept the journal. Most of the articles just assume that you're doing probability modeling. Journal of the American Statistical Association, sorry. Just assume that you're doing probability modeling and that you're running probabilistic search methods. So this started appearing in forensics about 10 years ago with groups in Europe and in Australasia publishing in. In fact, an MC-MC method for resolving two-person mixtures was published by James Curran from New Zealand 2 or 3 years ago. Niels Morling's group in Denmark has been doing the same type of research, and every one of these papers talks about how you do probability modeling of genotypes using all the quantitative data and representing it as multivariate, typically normal or gamma or some other sort of distribution, and then using probabilistic methods, typically statistical search, to search through and solve those equations. So this has become fairly normative science for people whose goal it is to extract as much information from the evidence as possible. Next slide. The second half is once you have a probability result, how do you quantify what you have? Claude Shannon brought this together in the 1940s with his mathematical theory of communication, in which he described a general theory. We now take the notion of bits and bytes as something normal. Bits were first described by Claude Shannon in this sort of work as a way of measuring information, the logarithm of the number of possibilities, where if any information source can be transmitted with noise, it can be received, and then at the destination the message can be known. It makes no difference whether it's digital information, computer information, DNA information, continuous telephone signals, which is what he traded this for, or images, such as video transmission. It's a general theory that you can quantify the information in a system. If you're willing to take more time and exploit redundancy, you can preserve virtually all the information that's present on the transmitting end. Next slide. This approach was also validated during World War II in a dramatic way by Alan Turing, who's often called the father of computer science. The Nobel Prize equivalent, the Turing medal, is named after him. He had used information, his own version of information theory, to quantify information and crack the Enigma code. The Enigma machine was a coding machine that the Germans had they believed was unbreakable. Alan Turing used information methods to decipher that code, which were turned into a number, I think hundreds of these giant they're called Bombe machines, that would decode, and the code was cracked. Thousands of German war messages were intercepted and properly decrypted, with the result many believe that was one of the major contributions to winning the war in Europe and defeating the Nazis. Next slide. In DNA, one of the holdovers for this was the likelihood ratio, which was first described by Alan Turing's group and used in cracking the Enigma code. The likelihood ratio is a way of quantifying in a very direct way what is the gain of information. What was your probability distribution before? You obtain information. Now what was your probability distribution afterwards? And what was the gain in information? In this way, as we see in quartz and in DNA, the notion of uncertainty can be quantified, testified to, and made quite precise. A number like a quadrillion to 1 as a math statistic is a likelihood ratio. Likelihood ratios were introduced in DNA from the very beginning by many people. I don't have room for all the references. There must be hundreds of papers on the likelihood ratio. Its use in quantifying information, different kinship analyses. You can't look at a journal article now where people are quantifying genotyping information from phenotypic or genetic DNA identification without seeing plots of log likelihood ratios. Most of the more recent effort, I think, has been going into how to explain the likelihood ratio to get analysts, particularly in the U.S., more comfortable with its use in court. In Europe and certainly England, New Zealand, Australia, it's required to use likelihood ratios. And so the effort now is how do you get more information preserving methods. Here again, the Gill paper states that the likelihood ratio ways of reporting are more informative and are to be preferred to inclusion methods, though in fact inclusion is a type of likelihood ratio. It's just less informative. It uses less of the available data. Next slide. So TrueAllele is simply a system that infers probabilistic genotypes and then matches them by quantifying the information with likelihood ratios. That's it. That's in essence all it does. From the user's perspective, data comes in, they ask questions, and answers come back out. What's going on is there's a large database server, and with a certain number of interpretation processors on it that run in parallel, that take the requests to solve each problem, and then we'll work on them doing statistical search of a probability model. That probability model includes genotype, the peak heights, the weighting of the different contributors, PCR stutter, relative amplification, perhaps most importantly, the variation of the uncertainty around every peak in the data. The data's never changed. There are no thresholds used. The data are the data. That's pretty much a given in modern probability calculation. But the uncertainty around the data can be calculated from the data itself within the model, and that's why thresholds aren't needed, because you're customizing the uncertainty to every data element in the data as opposed to using one blanket solution. The system's parallel for a very good reason that statistical sampling takes time. A typical mixture might run about 8 hours to sample 100,000 times from the probability distributions that are there. So that means that one processor could solve 3 items in one day. New York's computer, for example, has 16 processors, so they're solving 48 items on average. This is not reference samples, but evidence items, mixtures, in one day, which is about 15,000, 20,000 items per year, always running in the background 24/7. And if their caseload increases and they need to move up to 35,000 or 50,000 items, the system's expandable. It hooks into the same database. You just add more interpretation processors. Next slide. I just wanted to give one quick example because you'll be seeing this. I didn't stop at 15 minutes, sorry. The system infers genotypes up to probability and then quantifies the information with a likelihood ratio. So what do we see? This is data from an interesting case. I won't go into it, but there were 3 replicate amplifications of some very low template DNA with tremendous uncertainty. You can hear about this more. I think I described it in my Promega talk, 2010. But here at the VWA locus in blue, we're seeing the posterior probability distribution. The computer has no idea what you're looking for. The computations are done objectively with no knowledge of any suspect or any database of suspects. It just doesn't know. Mathematically, it can't know. It just doesn't know. And so all it can produce is a posterior probability distribution, shown in blue, posterior after it's seen the data. How do you quantify the information? There are 10 different ways to mathematically write down the likelihood ratio. They're all equivalent. But one that's particularly intuitive for lawyers and juries is to describe it as the gain in information, which is pretty much Turing's view of what the likelihood ratio was. So in brown, I'm showing part of the probability distribution across all allele pairs. There are really hundreds of possible allele pairs that could be here. And now we say, oh, well, the suspect has a 1418 as his allele pair. We didn't know that until this instant. So now we take our slider, we go over that point. We ask, what was the change in probability? What was the ratio of those probabilities? Well, the ratio of the blue to the brown, of the after to the before, is 6. And so there's a contribution of 6 in the likelihood ratio from that locus. Typically, we would take the logarithm of that and add the logarithms up at all 13 or 15 loci to get the exponent. Next slide. This is my last slide, which is, I hope, is a good introduction to some of the work that Russ and Joe will be presenting. So to validate the reliability, if any genotyping mechanism, human or computer, is inferring genotypes, a list of allele pairs is mathematically equivalent to a probability distribution of allele pairs, then the log of the likelihood ratio is, in many, many fields of science, throughout science, a standard measure of information. It has nothing to do with DNA in particular. It's used in statistics, natural language processing. It's used throughout science to measure how much information was obtained. And in our case, it translates all of the details, the complexities of the alleles, probability distributions of the genotype, what it's being compared to, the reference population, into one number. And the logarithm of that likelihood ratio number is a standard measure of information. So it can be used to validate reliability. Here, for example, this was a slide that I showed the subcommittee a year and 2 months ago. Here we see from New York State. These I'm only showing the true allele results. I'm not showing the human results because I'm just trying to keep it short. That was done last year, and it's in the slides that you have and in the papers. There's a whole section on this in the JFS paper that's appearing in November that hopefully you had a chance to look through. But in terms of what does it mean of how do you validate, well, we can validate efficacy and reproducibility. So here we see 8 different cases, and the information obtained by a match against the known contributor, or presumed contributor. In this case, it's a evidence cases. So here is 10 to the 5th, 10 to the 10th, 10 to the 15th, and so on, the logarithmic scale. And for each, the computer ran its statistical search in duplicate. The average efficacy, that is the mean peak height that's here, is 10 to the 13th, which, as you read in the paper, was about a million-fold improvement over the 10 to the 7th of human review of these 2 unknown mixtures without the victim known, 2 persons both unknown. And the reproducibility, you can visually see by seeing that the numbers are close. That can be translated mathematically into a within item standard deviation that asks what's the variation within each item. And that number is used to measure the reproducibility, which in this study was about 1/10 of a log unit. Okay, so was that helpful in bringing you up to speed? Or okay, thank you.